Hi there, this is day 27 and today's episode is brought to you by the letter V. And today, as you can see, we're going to be taking a look at potential difference. It's going to be a life-changing class today because after today, you will never look the same way at a battery again. You'll know exactly what that 12 volts means or what that 1.5 volts means. Now, potential difference is very similar to gravitational potential energy. Let's talk a little bit with regards to gravitational potential energy. You'll notice we got our spider back here. He's looking for cheek thrills. I guess he's nicely recovered from his octet knee replacement. Regardless though, gravitational potential energy. So this book right now, with respect to the table, zero gravitational potential energy. Because let's face it, I move it around and not too much happens. The spider isn't experiencing any kind of adrenaline rush. Okay, but if I do some work on it, okay, well, now it has some gravitational potential energy. And how do I know it has gravitational potential energy? Well, simply put, if I let it go, it moves on its own. Okay, now let's take a close look at a charge between our favorite piece of electrical apparatus, which is a pair of oppositely charged plates. So there's the positive plate, there's the negative plate, and we have a positive 1 coulomb charge in between them. And let's say the positive 1 coulomb charge is at the negative plate. Well, it has no potential energy down there because let's face it, if I grab onto it and I let go of it, well, nothing happens. Okay? So now suppose I grab on to that 1 coulomb charge and remember, it's positive, so these negatives are pulling it down, these positives are pushing it down. Okay? If I'm going to move that charge up towards a positive plate, okay, I'm definitely going to have to do some work on it. And once I do some work on it, I give it some potential energy. Because let's face it, if it's at the positive plate and I'm hanging on to it for dear life, and then I let it go, well, it's going to move on its own. These positives are going to push it down. These negatives are going to pull it down. It's definitely got potential energy up there. Okay, so whether you're talking about gravitational potential energy or the potential energy of a charge between some charged plates, they're pretty much the same thing. So now we know enough to define what potential difference is. Here's the official definition or official definitions of potential difference. Potential difference between 2 points, usually abbreviated with a capital V. You can express it one of 2 ways. You can say it's the potential energy of a unit of positive charge at one point with respect to the other point. Okay. The shorthand version would be potential energy per unit charge. Or you could say it's the work done in moving a unit of positive charge from one point to the other point. And again, the shorthand version of that is work per unit charge. And to be perfectly honest, though you kind of should keep both these definitions running in the back of your mind, this definition actually is a little more useful, and you'll see why in just a second. We will come back and we will show you exactly how to calculate potential difference. All right, so here's a little example that will show us exactly how to calculate potential difference. So once again, here's our favorite electrical apparatus, right? A positively and negatively charged pair of plates, and you can see they're 3 meters apart. There's a positive 2 coulomb charge sitting there in between them, and the electric field in between these plates is 4 newtons per coulomb. And you can see that it's down. And of course that makes sense because if you put a positive charge in here, well, these positives are gonna push it down and these negatives, they're gonna pull it down. And eventually we're gonna figure out the potential difference between these 2 plates. But for now, let's just see if we can figure out, like it says here, the work done in moving positive 2 coulombs from the negative to the positive plate. So first of all, convince yourself that if you have positive 2 coulombs of charge down at this negative plate, the negatives are pulling it down, the positives are pushing it down. You're really going to have to do work on it to get it from here to here. Okay, the question is, how much work? Well, what do we know about work? We know that work is equal to force times distance. And as you're pulling this thing along, again, you probably realize you don't have to accelerate this thing to the speed of light. If you're pulling it along at a nice constant velocity, that would be good enough. And of course, if you're pulling it along at a nice constant velocity, whatever force you're pulling it with, it's going to have to cancel out the electrical force on it. The force of these negatives trying to attract it back, the force of these positives trying to push it back. So the force you're pulling with is basically the same as the electrical force here. Okay, so the distance, well, we know what that is. It's 3 meters. Okay. We're not going to worry about the distance too much. What's the electrical force on that thing? Well, take a look. The electrical field is 4 newtons per coulomb. You got 2 coulombs. 4 newtons per coulomb times 2 coulombs, that's going to be what? 8 newtons of electrical force. So the electrical force on this thing is going to be the field times the charge. And then we just substitute in everything that we have to here. The electric field is 4 newtons per coulomb. The charge is 2 coulombs. The distance is 3 meters. You do that arithmetic, what do you get? 4 times 2 is 8, 8 times 3 is 24, and we're talking work, so it's going to be measured in Newton meters, or if you like, 24 joules. Okay, perfect. Now let's see if we can figure out the potential difference between the plates. Okay, well, you might remember from 2 minutes ago that potential difference is either potential energy per unit charge or work per unit charge. And as I say, it's usually more convenient working with the work per unit charge idea. So potential difference, that is the same as work per unit charge. So think about it. I did 24 joules on 2 coulombs worth of charge. How much work would I do on 1 coulomb worth of charge? Well, that's easy enough, right? The potential difference, the work per unit charge is going to be 24 joules divided by 2 coulombs. Well, that's going to be what? 24 divided by 2 is 12. What are my units going to be? Easy enough. This 24 is in joules. This 2 is in coulombs. And there is my potential difference. 12 joules per coulomb. Takes 12 joules of work to move a unit of charge from here to here. And of course, you never see 12 joules per coulomb written on a battery. You see 12 volts written on a battery. That's what a volt is. A volt is a joule per coulomb. Okay? So, what have we learned from this simple little example? Well, we've learned that if you want to figure out potential difference, you take your work and you divide by your charge. That's what that 24 is, right? The amount of work we do in the charge, and that's what that 2 is. It's the charge. Now, for whatever reason, I'm not sure why, probably because it's more convenient in most situations. You rarely see this equation written like this. It's usually written in a slightly different format, which is no big deal. You'll notice that if you solve this equation, if you solve it for W, if you take the Q over to the other side and it goes upstairs, this equation turns out to be W equals QV. And draw a box around that and reserve a couple brain cells for it, because you're going to see that a fair bit. Work is equal to charge times potential difference. Kind of makes sense, right? Take how many coulombs you have, multiply by how many joules per coulomb, and what you're left with is, well, the work in joules. And yeah, speaking of units, let's write that down. Okay. Units of potential difference. Well, a unit of potential difference is a volt, which is abbreviated with a capital V. And of course, a volt is equal to a unit of work, which is a joule divided by a unit of charge, which is a coulomb. All right, so what we'll do next, we'll talk about the fact that anytime you have a charge imbalance, you have a potential difference. All right, as I said before, anytime you have a charge imbalance, you have a potential difference. Here's your classic potential difference. It's again our favorite piece of electrical apparatus, a pair of oppositely charged plates, and of course, negative plate, positive plate, and yeah, obviously to move a positive charge from here to here, you're gonna have to do work on it. Okay? But you don't have to have positive and negative charges to have a charge imbalance. You can have, for example, a plate with a lot of positives and a plate with just a few positives. Think about this for a second. If there's a positive charge in between these two plates, the force from this plate pushing it that way is going to be a lot bigger than the force from this plate pushing it the opposite way. So the end result is, if you want to get this charge from here to here, you're going to have to supply some of your own force to balance off this one, and yeah, again, you're going to have to do some work on it. So from now on, the moral of the story is, whenever you see a car battery or any type of a battery, here's what I want you to see. I want you to see that positive terminal and that negative terminal, and remember that the positive terminal is basically just a collection of positive charges. The negative terminal is just a collection of negative charges. And yeah, you've got a charge imbalance. You've got a potential difference. And if you're talking about a car battery, well, the potential difference between those 2 points is 12 volts. It's going to take 12 joules to move 1 coulomb of charge from here to here. We will come back in just a second and we'll do a couple example problems. Good example, so we can work with some of the things that we've been talking about. It says a 12 volt car battery charges 2 plates as shown. So here's your 12 volt car battery, and what you should realize is that this is the symbol for electrochemical cell. One big line, one little line. And of course, a battery is usually just a whole bunch of electrochemical cells all put in series, one right after another. And usually an electrochemical cell, the big side is the positive side and the little side is the negative side. So same deal here. We know that this is the positive terminal of our battery, and this is the negative terminal of our battery. And you can see that our battery is connected to a plate on this side, and it's connected to a plate on the other side. Okay, so what's going to happen once you connect up this battery to our favorite piece of electrical apparatus, the large pair of oppositely charged parallel plates? Remember, the positive terminal of a battery is just a bunch of positive charges all clustered together. Okay. The negative terminal of a battery is just a bunch of negative charges all clustered together. What are these positives going to do to the electrons in these atoms? Well, they're going to attract them. And what's going to be left behind? A bunch of lonely protons. And of course, once these electrons, once they get to here, okay, once they're sitting right there, okay, well, they don't really want to go in this direction, right? Because the positives are actually pulling them up and the negatives are actually pushing them up. So once these electrons get to there, they're kind of reluctant to move. But that's where the magic of electrochemistry comes in. Okay? You can talk to Ms. Friesen about that for more details. But what a battery does essentially is it does work on these electrons, and it basically drags them from here to here, even though they don't want to do it. The battery, it does work on these electrons and drags them from here to here. And of course, once the electrons are down here, well, of course, you got a bunch of negatives, and they're going to repel the negative electrons in that direction, and the negative electrons are going to wind up on the bottom plate. Now, specifically in this situation, you can see that 0.5 coulombs worth of electrons have been transferred from here through the battery to here, because the charge on the top plate is positive 0.5 coulombs. The charge on the bottom plate is negative 0.5 coulombs. And what we want to do is we want to find the work done by the battery in charging the plates. So let's suppose that instead of these electrons getting transferred one by one, suppose all 0.5 coulombs worth got transferred at once. Okay, so you've got negative 0.5 coulombs worth of charge that are coming around here, and right now they are sitting there at the positive terminal of the battery, and they don't want to go to the negative terminal of the battery on their own, because let's face it, these positives are pulling them up, these negatives are pushing them up. So what the battery does, of course, it does work on these things, and it forces them, it pulls them from here down here. The question is, how much work? Well, remember this, W is equal to QV. The work done is going to be the charge, okay? And we're just interested, pardon me, in the magnitude of the work here. We won't worry about whether we're actually doing work on a positive charge or a negative charge. So we'll just throw in the magnitude of our charge, 0.5 coulombs. Work is equal to QV, the charge, 0.5 coulombs times the potential difference, which is 12 volts. Remember, you've got a charge imbalance here, okay? And it tells you, well, the charge imbalance, it is going to be representing a potential difference of 12 volts. Okay, easy enough. So the work is equal to the charge, 0.5 coulombs times the potential difference, which is 12. You do that and you get what? A half of 12 is 6. Coulombs multiplied by joules per coulomb, well, that's going to be joules, right? Units of work are joules. There you go. There is Okay, done. We'll come back in just a second and we will do a part B. Okay, so now we want to find, in part B of this question, the potential difference between these two plates. Remember, potential difference is the work done per unit of positive charge. All right, so seeing as we're talking about potential difference, the work done per unit of positive charge, even though it's electrons that actually move in a circuit like this, because remember the positives, the protons, they're stuck in the nuclei of the atoms. Okay. Just for the sake of doing the question, let's pretend that we take a positive unit charge, positive 1 coulomb's worth of protons from this negative plate, okay, up through the battery and deposit it on the positive plate. Okay. Again, even though usually negatives don't move, just for the sake of doing the question, let's pretend that, yeah, in this case we have positive 1 coulomb's worth of charge moving. Okay, so remember these negatives, well, they're going to attract the positive 1 coulomb from the plate to here. That's no big deal. But once the positive 1 coulomb, once it gets to here, once it's right at that negative terminal, it does not want to go in this direction. The negatives are going to be pulling it down, the positives are going to be pushing it down, so the battery has to do work on it. Once again, that's through the magic of electrochemistry. The battery's going to have to do work on it to get that positive 1 coulomb from here to here, and once it's here, it's a piece of cake. All these positives are going to push the positive 1 coulomb to where we want it to end up. So the question is, what's the potential difference between the plates? How much work is done on this 1 coulomb of charge in getting it from here to here? Well, again, the work done is equal to the charge times the potential difference. The charge is 1 coulomb. The potential difference, again, we know it's a 12-volt battery, probably a car battery. The potential difference is given to us, it's 12 volts. So the work is the charge 1 times the potential difference 12. There's the work done. 12 coulombs times joules per coulomb is going to be 12 joules, or 12 Newton meters, whichever you like. And I should mention right now that from now on, okay, if you see a situation like this, and you're trying to figure out the potential difference between these plates, you don't have to go through this whole rigmarole of dragging a coulomb of charge from one through the battery to the other. Okay, from now on, here's a shortcut you can use. If there's 12 volts of potential difference between here and here, there's 12 volts of potential difference between here and here. Okay, so from now on, if you see a pair of plates like this and they're hooked up to a 12 volt battery, you know the potential difference between the plates. You don't have to do any calculation. Just look at the battery. There's 12 volts between the terminals of the battery. That means there's going to be 12 volts between the plates. Done. Keep that in mind. It'll save you a lot of work. We want to take a look at one more quick example. Last example. This, I guess, is example number 2. What is the increase in potential energy of a proton that is moved through a potential difference of 120 volts? Now, before we do this, think back to what you know about gravitational potential energy. If you do work on something, you give it gravitational potential energy. And to tell you the truth, it's the same thing going on here, okay? Okay, so, what is the increase in potential energy of a proton that is moved through a potential difference of 120 volts? So I'll tell you what, the best way to represent a potential difference of 120 volts is with our favorite piece of electrical apparatus, a pair of oppositely charged plates. So there's a positive plate, there's a negative plate, and the potential difference between them is, just like it says, 120 volts. And of course, if you have a proton right here at the negative plate, well, right now, that proton, it has absolutely no potential energy. Because if you're holding it there and you let it go, well, it's just going to stay there. The negatives are pulling it that way and the positives are pushing it that way. But if you do some work on that proton and you drag it all the way over to the positive plate, well, at the positive plate, of course, now there's potential energy, because let's face it, if you let go of it, well, it's going to move on its own right back down to the negative plate. And of course, the increase in potential energy is going to be equal to the work done. Okay? So, no different from when you're talking about things in a gravitational field. Things in an electric field, same deal. The increase in potential energy, okay, well, that's going to be equal to the work done. Okay, how do you figure out work in this situation? Okay, work equals force times distance. That's not going to get you very far. That's pretty hard to deal with. Don't know the distance, don't know the force. How about this though? The work is going to be equal to the charge times the potential difference. Okay? What's the charge? Remember, your potential difference is 120 volts. That's 120 joules per coulomb. This 120 is 120 joules per coulomb. So we need our charge to be expressed in coulombs. We have a proton. The charge on a proton is, of course, one elementary charge, and that's equal to 1.6 times 10 to the minus 19 coulombs. So, basically, now we're ready to figure this all out. Our charge is 1.6 times 10 to the minus 19 coulombs. Our potential difference is 120 volts. You grind that through your calculator, and to tell you the truth, I don't have a calculator handy around here. Might have been the victim of the falling book. I'll let you do that. So whatever you get, you're going to get. Don't forget your units. Coulombs multiplied by joules per coulomb. Your units are going to be joules, or Newton meters if you like. Okay? And that's what it's supposed to be. Units of potential energy are joules. Okay, you are now ready to do an assignment with regards to this and cement it all into your brains. That will be posted along with this video. Bye for now.